is Irina. I can see her, so hello.
Now I hope you can also hear me.
Yeah, I can hear you now as well.
Okay,
That's fine. I can
so
see your screen as well.
yay, because as I talked earlier, things happen when you're online. Okay, so I think I'm okay to get started, right? Okay, so what I'm trying to do today is to make you forget about HTTP. Although you might say, hey, it's not okay to forget about HTTP because pretty much everything is HTTP. But to distinguish a little bit, I'm trying to say that forget about HTTP when it comes to service communication. And also do not do HTTP clients programmatically to get data from one microservice to another. So first of all, hopefully this will work. Um, who am I? My name is Irina Scurtu. You can find me on Twitter if you have questions on anything. I'm from Romania. I'm a software architect at a company called Endava, and I also organize a user group. And from time to time, I write articles on my blog. So we cannot talk about how to forget about HTTP or how to unlearn HTTP without remembering how HTTP works. So when you do an API to API call on the server side, because pretty much this is what we're focusing on, you're issuing a request, and that request is processed by the server, and hopefully you get a response back. And some folks in the industry say that is absolutely perfect to use synchronous HTTP calls. But how do you handle timeouts? How do you handle availability of the service that you are calling? How do you manage everything that related to availability, basically? What if one of your microservices is down and you're trying to call it from other microservice? How do you handle that? How do you make sure that everything is up and running? Is your system reliable when using HTTP calls in the classical manner between your microservices? How do you handle retries? Do you do retries? How many times do you retry? Are there any policies regarding how many times you retry? Maybe, but in any case, you'll need to find those by yourself. How do you handle the code coupling? I personally come from a .NET world, and we are working with something that is called Nugget Package Manager. We pack code there, and we search that code repository, and we get libraries from there. But trading HTTP clients with logic in them is not fine, because usually when you start to create an HTTP client that you were willing to share in order to reuse and all your different microservices, at first it's fine. But I tell you from experience that these clients, these libraries that you're sharing, tend to grow, and in the end, they will end up being just spaghetti of other libraries built in. Here, what you're gonna see is a small demo that in a 20 seconds time span, I'm gonna run an application to do a request to an API. And we're gonna see how many requests we're doing in the 20 seconds time span. And we're waiting for a bit because 20 seconds, it's an amount of time. And we'll see that in the end, the server that I'm calling from another server, well, we issues that number of requests. So 3,501 requests in 20 seconds. Okay, brilliant, right? But what if I told you that the server that I'm calling is not up, it's not running? Where is the reliability in it? And from the server that I'm calling's perspective, that server doesn't even know that something issued a request towards it. Basically, all the requests that I pushed, all the 3,501 of them are lost. So your system, in this case, is not reliable, even if it's a simple API to API call. So if we were to look at HTTP in general, HTTP is synchronous by nature. And more than that, with each HTTP request you're doing, either to send or to get data, it doesn't matter, it will make a new TCP connection. So if you're sending, you're trying, I don't know, you're calling in a loop, you're using in a loop an HTTP client to get data, then for each of those, it will make a new connection, which is costly. Another thing that is kind of bad about HTTP is that it has no retries out of the box. So if you need to implement some retry policies, you'll need to do them by hand. And now, depending on the world you're coming from, either .NET or Java or anything else, there might be libraries out there to help you, but still, there is absolutely nothing built in for that. And HTTP in general, it also has no delivery guarantees. You're issuing the request, but nothing guarantees you that that request is reach the destination. Also, location transparency. You'll need to tell where to call. You'll need to tell the address, the URL of the API you are calling. But fortunately, this is very good for public-facing APIs because it's familiar and also it's easy to debug. Because all developers somehow know how to do an HTTP request, either in tools, either from the browser, doesn't matter how. But it's common. Everybody has or coded at least one API at a certain moment and issued a request. But now we need to think about a few things. As developers, we do not think about what architects called non-functional requirements. As developers, we care about the functionality that we need to deliver, that small chunk of code that we have there. But these are very important stuff that we also need to have a look at and to have them in mind whenever we're coding an API or issuing API to API calls. Availability of the system, fault tolerance. Is our system fault tolerant or not? How about the network latency? What if you have bad internet connection or something happens across the wire and you're not getting data back? How about throughput? How many requests you are able to process successfully in a specific amount of time? Is the network reliable and the system in itself is reliable? How do you observe everything in your system when you have so many moving parts? Is your system also resilient? There are many strong words in here with many implications in the way you are coding things. But at least if you're not keeping these in mind, we should look at coupling. There is logical coupling when you're doing code sharing and logical and instantiating classes and so on, and temporal coupling. Well, the purpose of a microservice is to decouple, and microservices should be independent. But whenever you're sharing code for that small logic to make HTTP clients that get data from other microservices, you're creating a coupling. So now with HTTP, you also need both systems to be up. So if system A talks to system B, then system B needs to be up in order for them to have a successful communication, right? So in order to take care of this temporal coupling, you can evolve your architecture. So you can take another step and move on and forget about HTTP client calls between microservices and do another step. And that another step is called remote procedure calls, but through a message broker. And what is an RPC, or remote procedure call? It's a kind of an API call that is done through a different system, namely message broker. It will tie systems together, but also will preserve their encapsulation. You won't have code sharing like HTTP clients and packages. And also they will make the external system look local, and you will have no direct code dependencies. And how this such a RPC call will look is in the left-hand side, S, it's the sender, and the H is the handler. So what it does, you will issue requests or send messages to a queue. From that queue, the message or the request will be picked up and processed, and the response will be sent back through the same queue. Okay, so we'll have a look here at, in the left-hand side, you have a server that is waiting for a response. And on the right-hand side, you have a client that issues requests. And you will see, hopefully, so right hand sends request, left hand receives them. So you see it's pretty fast, and we almost, it's the same pattern, the 20 seconds time span, I'm having an eye that I'm increasing. And we also want to have a look at the throughput. With classical HTTP requests that weren't reliable and weren't received, we had 3,000 and something. Now we have 500 and something, which means 2,000 more requests on the same time span. And more than that, we kind of make sure that everything that we sent was received. So any request, it has an answer, okay? So what we get if you introduce a queue and we kind of do RPCs through a message broker. First of all, we won't lose those requests because those requests will remain in the queue. But and another thing that we gain is that we can add more consumers to process those requests. You can spin up more server instances. And you can apparently spread the load, and definitely you can increase the throughput. It almost doubled. But a bad thing that happens is that you will need to match the request to the response because it's still synchronous. But still, doing an RPC through a message broker, through a queue, is the next step that you can do to evolve your architecture. So start with HTTP and take another step. And the next step is to have RPC through queues. And if you want to take another step to have an even better architecture, you should look at messaging. And the concept of messaging, it's wide enough to talk about it for weeks, but it will definitely match into something like that. So in the traditional request, we'll have headers, body, and the verb for that specific request, either get, put, post, or delete. But if you try to match this to a message and what's a message in the messaging world, we'll see that the body becomes the actual content of the message, and the header will be somewhere on that envelope. We'll have no verb because everything that is in the messaging world is more programmatic as an approach. So messaging will give you loosely coupled integration. You won't need code sharing, and you also won't need both systems to be up, which is awesome. So since you won't require the both systems to be up, it also gives you some other power in terms of you can transform messages in transit. These messages can be transformed and enriched in transit. You can create virtual pipelines in order to transform or extract data from the messages. But you need to keep in mind that messaging systems, no matter what they are and who they are trading consistency for availability. But also they increase reliability. If you look at everything this is on the slide, I think there are strong and enough reasons to have a look at what messaging means. Okay, now you might say, okay, I got it. Sounds cool, but it also introduces complexity. Yeah, it does, but also comes along with a lot of non-functional requirements that are checked on the list of all the non-functional requirements you should have a look at, that I think it's worth the while. So what we have in here, it's a small demo. Again, I will issue in a 20 seconds time span messages, not requests this time, but messages. And behind the scenes, those messages won't be picked up and processed by anyone. But I will show you how now we have removed the temporal coupling. So assume that this console app is the client that issues requests, but the server is down. Let's see what happens. So I'm sending the 8th it message to a specific queue or to the server, but at this moment, the server is down. And since the server is down, there is no one to pick up the messages. So what will happen with them? Let's see. So that amount of messages that are processed in the 20 seconds time span. But now we need to have a look at the console in RabbitMQ because this is the message broker I chose. Everything is in there. So they are ready, waiting to be processed. But these messages are not lost, are there. And whenever there will be a system that will pick them up, those will be picked up, processed, and everything will be just fine. They are not lost. Hence, my system now is reliable. And more than that, the system is not not the system, the two components, the server that is supposed to process the requests is down, and my API, the app that issued the request, issues that many requests, and I decoupled them just by introducing something that supposedly is complex. Another step in the terms of evolution of this architecture is to have async message processing. Now you can leverage several queues through this message broker. For example, you can pump many requests in a queue, and from that queue, they will be picked up by a handler, but the response of the processing of those will be sent to another queue where they will be picked up by by the initial sender. But what happens here is that you will run into different patterns. You will need to dedup the messages or reprocess or make sure that each message is processed exactly once. But what also happens when you have a database, for example, you have higher throughput and you want to store the result of the processing in a database, you'll get in trouble. And you'll get in trouble because the database part has an issue. And that increased throughput and the process of the request faster, increase the reliability and everything, will move the potential issue to another subsystem, hence the database. The connection pool is limited, and you'll need to find some additional ways of handling the large amount of data processed. And one of those ways is to batch process the messages. I don't know, take them from the queue 100 by 100 or chunk by chunk, process them, store them in the database, and so on. Or I don't know, maybe introduce a semaphore. But anything has a solution in the end. Okay, so why I'm mitigating with this? Why I'm trying to convince you to use a messaging solution with microservices? Well, one of the many reasons is for the increased throughput. I think the numbers speak by themselves. Something in order of thousands, over hundreds, and so on. I think it's a difference is 10 times more. And also, another reason that you might consider using a message broker is you can scale down to reduce costs. For example, if you have a business that needs processing power for Black Friday or, I don't know, Christmas, you'll know for sure in the business that in a specific moment, you will have a peak of users or something like that. Then you can spin up consumers. You can spin more instances, and those instances will be able to process faster everything you have. And when you do not have that specific business need, then you can reduce the instances. I'm not talking about scaling the app. I'm talking about just adding another instance of the same app, not behind the load balancer or anything, but just spinning another one. And also a lot of utilities that they are brought. Scalability, performance. I think performance is worth their whiles, right? Fault tolerance out of the box. reliability out of the box, retries out of the box, they're there in the message broker. So what tools, frameworks, or systems you can use if you're talking about a messaging system or message processing middlewares? This is how they are called in the domain. One example is a simple queue, Amazon SQS. There are plenty of options: Mass Transit, RabbitMQ, ActiveMQ, Kafka, ZeroMQ, and so on and so forth. There are so many of them. And depending on their capabilities, they might win over others. For example, in RabbitMQ, it's written in Erlang. Queues are first in, first out. You can use ZeroMQ or any other system, but the principles apply to each and every one. If we were to look at the models in the messaging world, we have three types: queues, actor models, and message brokers. And the queues are the most easy. There's a sender that sends a message in a queue, the messages are ordered, and there is the receiver that pulls them. These are very useful for point-to-point communications, and messages are ordered and timestamped. So you'll definitely know whenever a message reach the queue. What it happens is that the receivers drags things from the queue. The messages are not pushed. There are two different ways of doing that. Such an example are Amazon SQS. In the actor model world, I'm giving examples in .NET because this is my favorite world, let's say, but you will find similar approaches in Java or others. In actor models, you are working with processes named actors that encapsulate behavior. So actors are more like message consumers. These message consumers can delegate and create new message consumers, can supervise their children, and in terms of guarantees of delivery, they have at most once delivery. These are born from reactive programming, which is a concept that is first mentioned in '73, tens of years ago. And they had their first version of an actor model in Java in '09, I think. For example, Orlan was used to build Halo 4 cloud services. There are a lot of things around this and a lot to talk about, and not the subject of this talk. If we were to talk about message brokers as a concept, message brokers are like control towers. They handle where they deliver the messages, they tell the airplane where to land. So essentially, in their bare bones, they're kind of a database that are optimized for handling message stream. And these message brokers are written in different languages. Nats, for example, is used by HTC, Siemens, VMware, and so on. And these message brokers, besides the capability of delivering different types of messages in different queues where those queues have at their end a consumer, they know how to handle message deliveries. So what happens is that something sends a message to a named queue or topic. At the end of that queue or topic, you can have one or many consumers. And the message broker also handles connection and disconnection very well. For example, at one moment, you can have one consumer, and the next second, you can have 10 consumers. The message broker doesn't care how many you have. It knows how to deliver and where to deliver your messages. And also super important, they also have the concept of a dead letter queue or poison queue, where the messages that cannot be processed are sent. You can configure this. For example, if you cannot process a message 3 times in a row, maybe you can discard that message, but you won't lose the message because that message will go to the dead letter queue. You can also retry the message, resend the message for processing, and so on. In terms of delivery guarantees, there are 3 types. And depending on what broker do you choose, they work on different underlying protocols. Same example, RabbitMQ and ActiveMQ. Guarantees, message delivery types. You can deliver one message exactly once, at least once, or at most once. And depending on what the business need is, you might run into troubles or not. But more than that, we talked about HTTP as a protocol. We need to talk about another protocol, and namely AMQP, Advanced Messaging Queuing Protocol. Advanced Messaging Queuing Protocol is asynchronous by nature. It has guaranteed message delivery, one of the three types. And for each message that is delivered through this protocol, there are no DNS resolves. And the routing through different queues is done programmatically. And another cool thing is that it has retries out of the box. So HTTP, no retries, you need to implement those yourself. MQP has retries out of the box. And another awesome thing with MQP and message brokers is that you can acknowledge, not acknowledge the messages processing. For example, you can take a message from one queue, or in fact, in message brokers, the messages will be sent to consumers, and the consumer simply receives the message and it needs to look at it and process it. Depending on, I don't know, values that you're sending in the message, you can say, hey, this is not good. This needs to go back in a queue. I will pick that up later. So it's up to you if you acknowledge or not acknowledge manually. In general, MQP has this concept of a channel, and I intentionally try to find the appropriate picture. Think about the connection. A connection is something that we know, a connection to the database, for example. And that connection is the external wiring, the coloring plastics in here. And inside that connection, you can have many channels. So you can send data through those channels, to the wires, the middle of the colored plastics. And this makes it very fast. And very fast means higher throughput. RabbitMQ message delivery, but I chose RabbitMQ just because it was the first system I ever worked with in the messaging world. But you'll find pretty much the same concept in any broker you look at. For example, you can add some routing keys to the messages, and depending on the routing key that you will add, it will be sent to a different queue where it will be picked up by a different consumer. So, for example, if you send something with images resize as a routing key, it will go to the resizer queue where it will be picked up by the specific consumer you assign there. Another option is the Fanout exchange. So basically, one message will be sent to different locations. It will be copied and sent automatically to different locations. Topic, for example, this concept you can find in Azure topics, right? It's pretty much the same, where you can add patterns to your messages, and depending on that pattern, it's like regex and so on. One message will go to Q1 or Q2, depending on what you send in there. For example, lazy orange rabbit, if you add that, it will go to the Q2, which has lazy.ds. But these three broadcasts, Fanout or topics or Azure topics and so on, the concepts are pretty much the same no matter the message broker. So I'm running out of time, but not before I show you these two books, Designing Data-Intensive Applications and Enterprise Integration Patterns, where you'll find pretty much anything on earth regarding the to the messaging. And I strongly advise you to have a look at those. It really helped me to understand a lot of concepts. They have a lot of useful information regarding the integration in the enterprise business. So thank you. So again, feel free to reach out to me if you have any questions. I will also look at the chat and stop my sharing.
Irina, thank you for that. There are no questions, but Anyway, to all viewers, you will receive Irina's email address. So if you have any questions for her, as she said, feel free to contact her directly.
On Twitter,
thank you, Irina,
I'm there.
that.
I will respond for sure. Thank you.
Okay, yeah. Yes, there are 2 questions. What about the size of the message to be posted to Rabbit MQ? Is the first question from Gaetano.
I do not know for sure the actual sizing in bytes or kilobytes for RabbitMQ, but for example, in Azure queues, it's still a queue. In the end, you can have small. It's intended to have a small data. If you want to transfer gigabytes of data, it won't work. You'll need to chunk those gigabytes of data into smaller pieces in order to send them. I don't know, 255 or something, 65, something like that. I need to look it up, but messages are intended to be something small in order to be transferred fast also over the wire.
Okay, thanks for that. And then there's another question. Could you discuss the differences between messaging systems and service meshes?
Actually, I cannot because I never used service meshes before. I will have a look at those and promise I will come up with an answer.
Yeah, this question. No,
it's not.
Yeah, the speaker side.
So I apologize for that.
No worries at all. No worries at all.
Not my area of expertise. Service meshes is a higher ground for architecture.
Don't worry about that. That was more than enough. Irina, thank you for that. It was very
Thank you for
interesting.
having me.
It was a pleasure, complete pleasure, obviously.